last lecture we ended with the definition of the nth homology of a chain complex. Yeah, so therefore this nth homology becomes a functor. Yeah, let me write that. So Hn is a functor. So Ch dot A to A. Hn is a functor where n is in Z. Is a sequence of functors. I mean, normally in practice you want to think of A as a module category, so the homology modules or homology groups, those are the common notation, common terminologies that we use. However, before that, like we covered snake lemma, which is perhaps the most important tool in our box for studying homological algebra, and 5 lemma also. And now what we are going to do is we will try to use this snake lemma to prove one very important property of these homology objects, the long exact sequence. So okay, let's recall something quickly. So A is given to be an abelian category. So therefore we can form the category of chain complexes from that. So the category of chain complexes is also an abelian category. Okay. So in that category we can define the notion of an exact sequence. So let me write down the statement that we want to prove. So this is one of the defining properties of a homology theory, or equivalently a cohomology theory. If there are certain properties which such a theory should satisfy, it should be a sequence of such functors indexed by integers which satisfy certain axioms called the Eilenberg-Steenrod axioms. And I am going to prove one of those properties. Yeah, I am not going to cover all the properties, but one of those properties. So this is the long exact sequence. So now here long means infinite of homologies. So given an abelian category A and a short exact sequence zero to A dot to B dot to C dot to 0 in the category of chain complexes there is a long exact sequence So what happens here? We have Hn of A dot, then Hn of B dot, then Hn of C dot, then Hn minus 1 of A dot, and dot dot dot, and over here it will be Hn plus 1 of C dot, and dot 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 in the opposite direction also. So this is the long exact sequence. Now possibly you can imagine that there will be a map from Hn A dot to Hn B dot. Yeah, this map is Hn, I mean let me name them F dot and G dot, then this is just going to be Hn of F dot, this is going to be Hn of G dot. How do we obtain this map from Hn C dot to Hn minus 1 of A dot? Any guesses? It's the delta from Hn to Hn minus 1, the snake lemma. Yeah, the snake lemma is supposed to provide us with this particular map, okay, this connecting map, but it's not very simple, okay. okay, we have to work a little bit hard for getting this. Actually the solution is that we have to use the snake lemma twice to obtain this long exact sequence. Okay, so very beautiful proof. So just the data is very simple, yeah, a short exact sequence of chain complexes. That's all is given and we want to figure out this. I'm just going to draw diagrams as proof, yeah, nothing more. Right, so the first one that we need to do is, suppose we are given AN, then we have BN, then we have CN. So what are the maps? Can you help me with the maps here? Is this an exact sequence? Is this an exact sequence? Yes. 0, AN, BN, CN, 0. Because A dot, B dot, C dot, that is a short exact sequence. So every column of that is also going to be an exact sequence. This is the column written as a row. Then similarly we have this AN minus 1, BN minus 1, CN minus 1 and 0. Okay. And vertically what map do we have here? Let's call it AN. Let's call this BN. Let's call this CN. These are the chain maps inside those chain complexes. So vertically we have something. Now I can take the kernel of this map AN. What do we call this kernel? Zn. Okay, let me quickly remind you of these things. So when we define this, there are three important objects when we are talking about a chain complex. Zn is the kernel of AN, Qn is the co-kernel of this. I think that should be Qn plus 1. Yeah, and Bn is the image object. So these three are important. So now we have, well, we are not going to use Bn because we already have a conflict of notation here, but we will only use Zn and Qn. So Zn is the kernel. So this is Zn A dot, this is Zn B dot, and this is Zn C dot. This is the kernel. So vertically we are completing it to a diagram. Then over here we will get the co-kernels, and this is Qn. Well, we can, I think, call it Qn minus 1. That will be easier for us to, so I should go there and change it. Whatever I had written earlier was correct, it should be Qn. Okay, so this is Qn minus 1 of A dot, then Qn minus 1 of B dot, and Qn minus 1 of C dot. And this is also surjective because we are just taking their co-kernels. So now what does snake lemma say? There is a map, like there are maps everywhere. Yeah. So the snake lemma guarantees existence of these red things. And we are using the full strength of the snake lemma because the map from AN to BN is also like this map Fn. Yeah, this is a mono and this is an AP. So therefore we are using the full strength. So we get an 8-term exact sequence of kernels and co-kernels. But this is not the end of the story. We have to continue using this part. The idea, the trick is that you break this sequence, 8-term exact sequence, into 2 parts. Ignore the delta map. You just get this Qn minus 1, Qn minus 1, and then you get Zn, Zn, Zn. And you have to adjust the indices in such a way. So let me draw the other diagram now. So here we are going to get Qn, let's say. So Qn A dot, yeah, Qn dot, Qnc dot, and well, this 0 is going to be useful for us, and at the same time we need this Zn minus 1 A dot, Zn minus 1 B dot, and Zn minus 1 C dot. And vertically we will have maps. So why do we have maps vertically? Can you understand that? Qn A dot is the quotient of An. So from An we must have a map to Zn minus 1 A dot. Do you agree with that? If you look here vertically, yeah, around this point, An minus 1. So there is An minus 1 coming down, little An minus 1. So the composition of An minus 1 with An is 0. So therefore, there should be a map from An to the kernel of little An minus 1. So there should be a map from An to Zn minus 1 A dot. But now look here. When you take its composition with the previous one, then that must be 0. I mean, we can see that it must factor through the co-kernel. If two elements have the same thing, if their difference lies in Zn A minus A dot, then they must map to the same element. So therefore, it must factor through the quotient. So therefore, we have induced maps from Qn A dot to Zn minus 1 A dot, Qn B dot to Zn minus 1 B dot. Yeah, this is just induced from An. We are not doing anything else here. And then, if you understand the definition of homology properly, then this is actually just Hn A dot. The kernel of this is going to be the same as the homology group. And over here, the co-kernel of this, we saw the two definitions. Yeah, one is symmetric. So you can see that this exactly gives us what we need. So this will be Hn A dot, Hn minus 1 A dot. This will be Hn minus 1 B dot, and this will be Hn minus 1 C dot. And this map will be surjective, surjective, surjective. All of these are surjective. I shouldn't be drawing this middle one. And then again apply snake lemma to this particular diagram to obtain this. And when you vary n, then you can combine these. Okay, Hn is itself a functor, so 4 out of these 5 arrows you know what they are. But the delta comes from this, the middle arrow. And you can see, like, if you take Hn minus 1 at the top here, Hn minus 1, Hn minus 1, Hn minus 1, then you will get Hn minus 2, Hn minus 2, Hn minus 2. So you can actually just glue those things together. Got the idea? Very beautiful application of the snake lemma to get a long exact sequence of homology groups. If you have studied algebraic topology, then there is also a long exact sequence of homotopy groups. Yeah? And also for homology, I mean the long exact sequence of homology of topological spaces, that just comes from this. Either singular homology or simplicial homology, doesn't matter. So this is the end of the proof. Yeah, we don't have to do anything else, just snake lemma applied twice. I was talking about algebraic topology, right? So the main thing that we study in algebraic topology, that's the beginning usually, is the concept of homotopy, right? So what happens, like, given if you have studied simplicial homology or singular homology, then you know that from any topological space, we first obtain the singular complex, or just the complex of simplices, like the abelian groups generated by n simplices, though that will be your nth entry in the chain complex. Now, what happens when you have two continuous maps? This is a functorial assignment, right? Like if there is a map f from x to y, then that will give you, I mean, maybe I should just write it as an aside. So given f from x to y in top, and we get f dot from the singular complex to of x to singular complex of y. So what if we have two continuous maps that are homotopy equivalent? Then their images in this category of chain complexes, so this is happening in the category of chain complexes over abelian groups. Yeah, that's how we normally define it. So if two maps are homotopy equivalent, then actually they can also be termed as homotopy equivalent in the category of chain complexes, provided we define the notion of homotopy of chain complexes appropriately. So let us do that now.
What is S dot X?
That's the singular complex. If you don't know, then I mean, if you are given a simplicial complex, then it is very easy to understand. Like that's the simplicial homology I'm talking about. So then you take the abelian group at nth level. It's the abelian group generated by all the n simplices, and then the boundary and face maps. Yeah, they give you these maps between the corresponding abelian groups. It's a free abelian group at each place. Singular homology is defined similarly. Okay, so these are just continuous maps from spatial topological spaces. So there is a concept of chain homotopy motivated from this notion of homotopy in algebraic topology. Okay, so what is chain homotopy? So given f dot comma g dot from a dot to b dot, say that f dot is chain homotopic to g dot, written that same notation as homotopy. Yeah, f dot is chain homotopy equivalent to g dot if there is a collection Hn from An to Bn plus 1 for n in Z of morphisms in A such that, so these are called degree 1 maps, okay, degree 1 because it goes from An to Bn plus 1. Normally our chain maps are degree 0 maps, they go from An to Bn. Here we are not asking for any commutativity. That's also another point worth emphasizing. Yeah, this is just an independent collection of, a loose collection of maps indexed by natural number, by integers, such that, now this condition is important. So Gn minus Fn is equal to Bn plus 1 Hn plus Hn minus 1 An. Okay, now I have to show you what these things are. So here we have An, An minus 1, An plus 1 and so on. This map is An plus 1, this map is An dot 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 this is dot dot dot, this is Bn plus 1, this is Bn, this is Bn minus 1 and dot dot dot. So this is Bn plus 1, this is Bn. Okay, so F and G are here. This is Fn, this is Gn. This is Fn plus 1, this is Gn plus 1. This is Fn minus 1, this is Gn minus 1. Okay. The homotopy is actually a collection of maps like this. So this is Hn, this is Hn minus 1. So they have to be compatible in such a way that you see a parallelogram here. Yeah, An to Bn plus 1 to Bn and An to An minus 1 to Bn. So there are two different ways of reaching Bn, not going via Fn and Gn. So the sum of those two ways is the difference between Fn and Gn. If you verify, if you do this topological construction, yeah, that the map is actually induced from a topological map between topological space, and those two maps are homotopic, then you will get this automatically. Okay, I'm not speaking so much about topology because this is not a topology course, that's all. But if you verify, then you will be convinced that this indeed is related to that. So here notice that this particular thing is, this particular relation f dot related to g dot is reflexive. Can you convince yourself of that? Why is f dot related to f dot? Because I can choose Hn to be 0. Yeah, because Fn and Fn minus Fn is 0. So therefore 0, 0 will work. Then this is symmetric because I can always, like, if H works for f dot to g dot, then minus H will work from g dot to f dot. And then it's also transitive. You will have to do a little work, but I'm just going to write that this is, yes, you have to do take some combination, is indeed an equivalence relation. On the category of chain complexes, right? This is our category, and then I have this A dot B dot. Okay, I mean, you can verify that. I shouldn't be saying indeed, yeah, but I think I convinced you that it is this. In fact, it is a congruence relation. Okay, so what does that mean? It is a congruence relation means that whenever f dot, so let me write it. So if f dot is related to g dot, and there are two other things, yeah, let's say k dot and l dot, and if k dot, f dot, l dot and k dot, g dot, l dot are defined, I mean, I'm writing dot dot, are both defined, then they are also, so from both sides this homotopy equivalence extends. Left composition, right composition. Now try to remember something from the beginning of the course. Whenever you have a congruence relation on home sets, then what can you do? We can quotient out by that. And that quotient is called the homotopy category. Okay. So define the homotopy category of the category of chain complexes to be the category, let me also give you the notation. This is K dot A, it is CH dot A quotiented out by the homotopy equivalence relation. Okay, this is the homotopy category. Okay, actually, if you really want to think about the corresponding version of the homotopy category of the category of topological spaces, then this is just a naive version. Yeah, this is not the ultimate thing that you really need. The ultimate thing is, in fact, the derived category. I'm going to define it as well. So this is just K dot, CH dot to K dot. And okay, so let quasi of A, no, I should say chain. Quasi of chain, chain complexes denote the collection of all quasi isomorphisms between chain complexes. Okay, i.e., I haven't defined what is the meaning of quasi isomorphisms, i.e., maps f dot from A dot to B dot such that Hn of f dot from Hn of A dot to Hn of B dot is an isomorphism for all n in Z. So the chain maps which induce an isomorphism between chain complexes. Okay, these maps are known as quasi-isomorphisms. And quasi actually suggests that we would like to invert them. And we have already discussed one method of inverting, formally inverting maps. You remember the method? What do we call it? Localization. So exactly. So we would like to localize our category of chain complexes with respect to quasi-isomorphisms. And then when you localize at that, then from that localized category to the category of, to the original category A, we will get Hn. The homology functors should actually factor through this. And, okay, if you are worried about set theoretic conventions, like set theoretic issues, I shouldn't say conventions, then if A, the curly A, happens to be a small category, small abelian category, then there is no issue in directly inverting quasi-isomorphisms. Okay, so let me write that. So if A is small, then define, then the localization, let me call this Q, okay, like for a small, this, then the localization Q inverse A is well defined. And we call call it the derived category of A. Okay, so this is the, sorry, then the localization, sorry, I'm not thinking about it properly. This, okay, Q inverse of CH dot A, because we are inverting morphisms from that. Yeah, so this is called the derived category of A, denoted D of A. And we are also going to write the dot at the bottom to denote that this is the homology version, not the cohomology version. However, yeah, if A is not small, then you can't really do this process. Because if you remember, then we have that zigzag. How did we define localization? That we have to take one arrow which is not necessarily invertible, and you have to go along that arrow, and then another arrow which is invertible. So we defined it as sinks, if you remember. Yeah, this arrow is not necessarily invertible, but this one is. And then you have to go through finitely many such things. And then we saw that, thanks to Gabriel and Zisman, that if it is a multiplicative system, left or right, then we can do everything very well. Okay, so if A is not small, if A is large, then this Q inverse CH dot A will not be a locally small category. It will go beyond our control. So therefore, the correct definition is this. So subject to the next result, okay, I haven't stated it yet. The correct definition of the derived category of A is the localization of the homotopy category K dot A at the collection of quasi-isomorphisms. So it becomes a two-step process. Yeah, so what happens really is you have A, and then from there you have CH dot A. From CH dot A we get K dot A, and from K dot A you localize at Q, or images of Q, yeah, under homotopy category, localize at Q to get the derived category like this. And this process works for any A, irrespective of whether A is small or large. Okay, so there is only one missing point here, subject to the next result, and I haven't stated the next result yet. And that next result is the property which is very common, I mean, very commonly known as homology is homotopy invariant. Okay, so homology is homotopy invariant. Any questions about this? The first step is just the quotient, and the second step is localization. We have discussed both these things, and the quasi-isomorphisms will form a multiplicative system at the homotopy category level, but not necessarily at the chain complexes level. Okay, so next theorem, which states that homology is a homotopy invariant. What do you expect this result to say?
CH to D dot A is the same as CH to K dot A to D dot A.
No, not that. But if there are two chain maps which are homotopy equivalent between two chain complexes, then they will induce the same homology, same maps between homologies. Okay, so let me state it properly. So if f dot and g dot are maps from A dot to B dot, satisfy f dot homotopy equivalent to g dot, then hn f dot is isomorphic to hn g dot for each n. Just like in topology, we can also describe when two complexes are homotopy equivalent. Yeah, in topology, what do we say? We are given topological space X and space Y. Yeah, so from X to Y, see here, yeah, X to Y we have a map F, and from Y to X we have a map G. So G composed with F. So if G composed with F is homotopy equivalent to identity of X, and F composed with G is homotopy equivalent to identity of Y, then we say that X and Y are homotopy equivalent. Here we are talking about the map version, but we can also talk about the object version, that Hn of A dot will be isomorphic to Hn of B dot if there is a homotopy equivalence between them. Like F dot going in this direction, G dot going in this direction, such that Gf dot is homotopy equivalent to identity and Fg dot is homotopy equivalent to identity. Okay, so this is what we want to show. Is this clear? Okay. So the proof for this is quite simple actually. Okay. So we are given a system like this. Yeah, Fn and Gn. I'm not going to draw another diagram, just have a look at the existing diagram. So what do we know? This particular expression. Okay, this expression. Now what will happen if I combine it with, I compose it with the inclusion and surjection maps. So let us see this. From diagram, double star, where I am labeling the diagram double star now. Yeah, this is our double star. We have Gn minus Fn Gn minus Fn is equal to Bn plus 1 Hn plus Hn minus 1 An for all n. Okay. Then Qnb composed with Gn minus Fn composed with Zna. Now Zna, you understand what it is? It is the kernel of An. and Qnb is the co-kernel of Bn. Okay. So Qnb, this what will this be? This will be Qnb Bn plus 1 Hn Zna and plus Qnb Hn minus 1 An Zna. Okay, can you tell me what this is? What is An Zna? 0. And what is Qn Bn plus 1? 0. Yeah, so these two are 0, so therefore this is 0. Okay. Now if you notice this, so therefore what do you get? That Qnb composed with Gn Zna is equal to Qnb composed with Fn Zna for each n. Now you just have to recall the definition of homology. But Zna dot, yeah, then An, then Bn, and Qnb dot, yeah, so this is Qnb, and this is Zna, and this is Fn. Okay, but this diagram actually commutes. You can put the homology groups here. And then this embeds again. So this is Hn of F dot. But this diagram commutes. This comes simply from the definition of homology, the symmetric version of the definition of homology. So this diagram commutes. What did we just see? From the previous line, we can read that if I replace this Fn by Gn, then nothing is going to change. So therefore, even if I replace Hn F dot with Hn G dot, then also I will get the same thing. In homological algebra, it is very important to play with these concepts, yeah, with these diagrams. Without that, you won't be able to appreciate what's really happening. Okay, so this diagram commutes is the only reason that we don't need to worry about it. This is a very sleek proof. And subject to this result now, it makes sense to define the derived category as the localization of the homotopy category at quasi-isomorphisms. Because quasi-isomorphisms will remain quasi-isomorphisms when you quotient out by homotopy equivalence. You understand? Because, yes, I can repeat. So, quasi-isomorphisms are the morphisms which induce isomorphisms between homology objects. Now, because homology is a homotopy invariant, even if I quotient out by chain homotopies, it really doesn't matter. I will still have like quasi-isomorphisms, their equivalence classes. The equivalence class of a quasi-isomorphism will still be a quasi-isomorphism, and K dot A is much more manageable category, and quasi-isomorphisms will form a multiplicative system there, so you can localize, yeah, formally invert this, and then what you get is the derived category. However, now notice something, that so far we haven't really connected one the category A with the category of chain complexes. I mean, obviously, if I'm given an object, let's say C of category A, then I can form a chain complex which has only one C and the rest of them are 0. Yeah, so that can be thought of like we can always say that this is happening at 0th position. At the 0th position, the object is C and everywhere else it is 0. That is definitely an embedding of the category A into the category of chain complexes. However, that particular embedding is not necessarily well behaved with respect to homotopy. We want some nice embedding of A into K dot A. Okay, so we want to look at one object of category A as a homotopy equivalence class of chain complexes, and possibly with some more properties. And the thing that is going to help us in doing so is our next concept of projective resolutions. I do not remember if we ever defined a projective object in the class. So let me define it. So say that, I mean, this definition doesn't really require an abelian category or additive category. Say that an object P of a category, I'm just going to use the notation A, is projective if AP blank preserves epimorphisms. I mean, okay, of a locally small category, maybe I should say that. AP blank, so this is happening from A to, in this case it is happening to R, but if you have locally small then you can also do it to sets. If this preserves epimorphisms. So this is the definition. Now, if A is abelian, then the following are equivalent. The first condition is that A is projective. The following are equivalent for an object P of A. Okay. The first condition is that P is projective. Then second one, P is AP blank from A to AB is exact. And the third condition is that any AP from Q to P is split. If you are working in a module category, then you can actually add one more condition, that it is a direct summand of a free module. Okay, so but I'm just going to prove this. So 1 if and only if 2 is quite easy to see. Home functors, yeah, I mean this is the enriched home functor, right? AP blank is the enriched home functor, because we are talking about abelian categories which are additive, hence pre-additive, and pre-additive means ab-enriched. So we are taking this functor down to the enrichment. So this functor is always what? This functor is always lex. It always preserves limits, kernels. So AP blank is a lex functor. Home functor always preserves limits. So it is exact if and only if it preserves co-kernels. And because co-kernels are precisely epimorphisms, thanks to the condition in an abelian category that all epimorphisms are normal. So, if and only if it preserves epimorphisms. Okay, so this is a simple proof, just one line. Now, if you want to see 2 implies 3, suppose it is exact. Oh, I mean, sorry, 1 implies 3. Let's do 1 implies 3. That's better. Okay, so you want to show that any epimorphism is split. Well, it preserves epimorphisms. So you can say this is Q to P, and then this is my P, and I take identity to P. Now, identity is an epimorphism. Sorry, this is an epimorphism. So therefore, there must exist some map here such that the diagram commutes. That is condition 1. So there exists such a thing. So that will be the splitting. Yeah, preserves epimorphism means that whenever you are given a surjection and a map from P to the codomain, then you can lift it to a map from P to the domain. So that's precisely what we have written. And 3 implies 1 is also simple. Suppose we are given, now we want to show that. Now suppose we are given A to B. This is an epimorphism. And then we are given a map like this from P to B. What we do is construct a pullback. Okay, so this is the pullback. Let me call it Q. This is an epimorphism. So in an abelian category, we know that pullback of an epi is AP. So this is an epimorphism. So therefore, by property 3, there will exist a map in this direction. So if you want, I can write all these names. This is G, this is F, this is H, this is K, and this is S. So there is S over here, which is a splitting for K. Then what will happen? The required map is, yeah, so what happens with FKS? FKS is equal to GHS. But FKS is nothing but F. So we are done. Yeah, we wanted a factorization of F through G. So we got it. So this is the proof that projective objects in an abelian category have got multiple different characterization. And some examples. So free modules are projective. And direct summands of free modules are projective. I already mentioned that. And then if you remember, we have talked about projective objects in, like, there are enough projectives in a module category or in a Grothendieck category. So let me just recall that. If A is Grothendieck, then A has enough projectives. i.e., for each A in P, in A, there is an epimorphism for some projective P. I mean, in a normal scenario, like in a module category, you can always do it by taking a free module. A free module always covers a given module. You take a set of generators and then take the quotient. And if you take a set of generators, then basically you are going to take a direct sum of so many copies of the ring. And because we have seen that every Grothendieck category is a localization of a module category, so you can have the same property here. Yeah, the images of free modules under the localization will work. Okay, so this is what we want, that it has enough projectives. Now, if it has enough projectives, then we can do something very interesting. Okay, so given A, so what is projective resolution now? Now let's try to see this. So given A, construct this. So we are given A, okay, then we have some projective P0 and a surjective map. Okay, surjective map. So I can take the kernel, let me call this epsilon. This is a standard name for this map, epsilon. So let me take K0, which is the kernel of epsilon. Then from K0, like K0 is some other object, so I know that there will exist some epimorphism onto K0 from a projective module. Okay, so this is that particular thing, and then this particular map will also have some kernel. Okay, then for this K1, sorry, this should be K1. For this K1 also, I will have some P2 which maps onto it. And then I can take its kernel as K3 and K2 and so on. You can see. Now, what do we know here? So actually, this composition from P1 to K0 to P0, that gives me a map here. Then this map is here. Then this map is here. So these are called, yeah, let me call this map little p1. This is my map little p2. This is my map little p3 and so on. So you can construct this assuming that A has enough projectives. So in particular, if it is Grothendieck, assuming A has enough projectives, we can construct this. Any questions so far?
Yeah, so these projective resolutions aren't like unique up to.
Yes, but I haven't even defined a projective resolution. It's not unique, but there is a relation between any two projective resolutions. And what that is going to be is that they are going to be homotopy equivalent. That is the motivation we started with. Okay, so what is the projective resolution? Yes, so the projective resolution thus constructed is the complex chain complex. By complex I just mean a chain complex. This one, P2 to P1 to P0 to 0. Is this complex, which is actually in the category of chain complexes over the projective objects in A. So we are actually taking much smaller collection. The projective objects, they form an additive category. They do not necessarily form an abelian category. Direct sum of projectives is projective. Yeah, so therefore they form an additive subcategory. And we are not allowed to use anything else in this particular category of chain complexes. Okay, so this is the projective resolution. and has the property that what is Hn? Has the properties, I should say, two properties, and has two properties. The first one is that Pn is equal to 0 for all n less than 0, first one. And second one is that Hn of P dot is equal to either A or 0 depending on whether it is 0 or otherwise. So what we are doing is we can recover the object A as the zeroth homology, because you can see what is the image of the map from P1 to P0. How do we define homology? Kernel modulo image. Yeah, what is the kernel of the map from P0 to 0? It is everything, P0. And the image of the previous one, that is precisely K0. So P0 modulo K0 is isomorphic to A, because this is an exact sequence. K0, 0, K0, P0, A0. And at any other location, if you compute the homology object, then that turns out to be 0, because we are just defining it to be that.
Do you mean for all n greater than 0?
No, actually even further, right? This is, I mean, this is also 0 on this side. Yeah, once I say 0, then it continues to be a 0. It's a chain complex, so it has to be indexed by integers. So only at one location the homology is A, so you can recover A up to isomorphism. But then the question that Vineet asked already, that what is a projective resolution and what is the connection between any two projective resolutions? So let me first define a projective resolution. A projective resolution of A is any complex P dot in CH dot of proj A satisfying 1 and 2 above. Okay, so it has to satisfy this. So now, what is the relationship between any two projective resolutions? We are going to answer that question using homotopy. Okay, so suppose we will go a bit slowly for this. We are going to prove some intermediate result before we can actually prove what we want. So this is a new theorem that we need. So suppose E is a morphism from A to B, is any morphism in A. Let P dot and Q dot be, let P dot and Q dot be projective resolutions of A and B respectively. Then first one, that we can actually lift, then there is a chain map F dot from P dot to Q dot such that Hn of F dot, H0 of F dot is equal to E. So this particular morphism can be lifted to a morphism between chain complexes. And then the second one is that any two such chain maps, I mean chain maps which satisfy the first condition, are homotopic equivalent. Okay, so therefore, now again, what we are writing is an existence and uniqueness theorem only for parallel pair of maps, but you already know how to convert it into objects. For that you are given one map from this to this direction, another map from this to this direction, such that the composition is homotopy equivalent to identity on both sides. Okay, so let us try to prove the first result. So there is a chain map such that we can do this. Now here, if you have multiple colors, it will be useful to write. So let us see what whatever I'm writing, you will be able to see this. So I'm again going to do the same thing. So K0 to P0, that's the kernel. Then P1, this is a surjection, right? Then K1 is the kernel, then P2 is the surjection, and so on. Then from A to B, we have a map which is E. Then here I have Q0. Yeah, this is epsilon A, this is epsilon B. Then this is L0, let's say. Then this is Q1, surjection. This is L1, inclusion. This is Q2, surjection, and so on. Now what we need is a map from here to here. Okay. So first of all, I'm going to use green and red. Yeah? So the green arrow from, so observe this condition. Q0 to B, epsilon B. It is called the augmentation map. Yeah, this augmentation map is surjective. I mean, it is an epimorphism because there is a 0 at the end. So therefore, any map from P0 to B can be lifted to a map here from P0 to Q0. So the green arrows exist by projectivity. Okay. Now, it's not just this. So let us call this F0. Okay. This is F0. Now what happens? See this. K0 to P0 to A. That composition is 0 because K0 is precisely the kernel of epsilon sub A. So therefore this composition is 0. So if you go along E further, then that is also 0. So therefore this way is 0. So then what can you say? That this F0 followed by this kernel map, that must factor through the kernel of epsilon B. So therefore that's your next factorization. So the red arrow exists by factorization through kernel. Okay, then we continue doing this, we will get a further map. Now this is exactly the same situation. You can think of this K0 to L0 as new map E. And then repeat the argument, you will get F1 here, you will get F2 here, and you will get some maps in between. And the process will continue. So you can always do this lifting. These are some of the most beautiful ideas in this area. Yeah, that you can always lift these things. So this is the proof of the first one. I mean, you can check that H0 of F dot is precisely E. That just follows from this. Yeah, the co-kernel is A, the map is then the co-kernel at the bottom is B, and therefore you get precisely this. Okay, so now we have lifted, we were able to lift this in the first place, and now the second proof. Now, if we are given two chain maps, then we should be able to show that they are homotopy equivalent. So one such diagram looks like this. So I'm going to again draw another diagram, but a much smaller version now. So we don't want to talk about all the intermediates for the top arrow, top diagram, and the bottom one, we will need all of them. So this is Q0. Then here I will still continue to take L0. Yeah, this is the kernel, then this is Q1. Then this is a surjective map, this is L1, this is an inclusion, this is Q2, this is a surjection. In the top one, we don't need all of them. We can write, but we don't need to. Then this one we are going to call, this is P1, this is epsilon A, this is epsilon B, this is P2. Yeah, this particular, this whole thing, it's Q1, little Q1. This whole thing, this is Q2. Okay. Now vertically we are given P0 to Q0, there are two maps, little f0 and little g0. I'm not going to write all of both of them, but instead I will simply write f0 minus g0. And over here, whether I put f0 here or g0 here, the diagram commutes with E. So E epsilon A is equal to epsilon B f0 is equal to epsilon B g0. So therefore, what should I write here? 0. Yes, E minus E. So that is 0. So it is the 0 map. Okay, if it is the 0 map, then what do we know? When we are going from P0 to A to B, then we are just going to get 0. So therefore, P0 to Q0 to B also we are going to get 0. So therefore, there must exist a map through kernel. Right? So let me use the red arrow. There exists a map through kernel. Okay. But Q1 to L0 is a surjection and P0 is projective. So therefore, by projectivity, there will exist a map here, and this map is what I am going to call my H0. Does the notation ring bell? H0, that's the homotopy. Yeah, so P0 to Q1 we obtained something. Now what is the vertical map? Well, that's the only thing you need to understand, that this is G1 minus F1 minus H0 P1. The reasons are still the same, yeah? I mean, green arrows and red arrows exist for the right reasons. Okay, so G1 minus F1 minus H0 P1. Does this diagram commute? So Q1 G1 minus F1 minus H0 P1 is what? Well, I can write it. So Q1 G1, what is Q1 G1? Q1 G1 is, no, Q1 G1. So it should have to do with G. Yes, G1 P1, G0 P1, G0 P1. Then Q1 F1 will be F0 P1. And then minus Q1 H0 P1. So look here, P1, H0 and Q1. Now this triangles, they both commute. So therefore, Q1 H0 is nothing but this vertical map, F0 minus G0. So that is F0 minus G0 P1, which is just 0. So therefore, this, what happens that you have reached the original situation. Exactly. So it must factor through kernel of Q1. Right? So Q1 composed with this is precisely this. So therefore, it must factor through the kernel. So there will exist a map here, and therefore there will exist a map here, and then the process will continue.
For showing that f dot is homotopy equivalent to g dot, we need to
Find the homotopy.
yeah we need to like show that gn minus fn is equal to
Gn minus Fn is something. So that's,
how do you know that?
so H0 P1 and then Q2 H1, their sum will be G1 minus F1. And yeah, that's how it will continue. Which is precisely the definition of chain homotopy. So this is the end of the proof for the second part. Now, as a consequence, we can show that any two chain, like any two projective resolutions are also homotopy equivalent. So what did we show? Like if we want to combine this data into a single result, so we have shown that projective resolution is a functor, from A to K dot of proj A. In fact, it's not just K dot, it's K bigger equals 0 of proj A, which means not all indices are allowed to be non-zero. Yeah, can replace K dot of proj A by K bigger equals 0 proj A. Okay, so we are landing inside something very specific. And I mean, there is further theory. Yeah, so this is just the theorem which I'm not going to write a proof for, but the derived category with chain complexes only in this part, d bigger equals 0, is equivalent to this. So this is the true homotopy category. I said that the homotopy category K dot A is the naive version, but the derived category, this particular derived category, and you can see the arguments. Yeah, the arguments, like in the derived category I'm using A, whereas on the other side I'm using proj A. Proj A is just an additive subcategory. It's the full subcategory on projective objects. Any questions so far? Okay, so this is, you just accept this this particular result without any proof. Now I'm going to pose a question. So suppose A and B are abelian. A has enough projectives. And F from A to B is an additive functor. Then, given a short exact sequence 0 to A to B to C in A, how do we extend FA, FB, FC to a long exact sequence. Okay.
Projective resolutions and then the first thing
Projective resolution and
which we did.
what is the first thing that we did?
That short exact sequence of chain complexes gives us a long exact sequence.
Short exact sequence of chain complexes gives us a long exact sequence, correct? But do we have a long exact sequence yet? Do we have a short exact sequence of chain complexes? Your answer is correct, that we have to construct this, but
The previous lemma, like you have maps from A to B, then they become maps from projective resolution of A to projective resolution of B.
well, we'll construct that. Yeah, that's called the horseshoe lemma. I will draw a horseshoe shape and then we will figure out what those maps are. The things that you construct on this side, yeah, I mean, if f is a Lex functor, then what will happen? Then you will get a 0 here. So then you can continue it to be 0, 0, 0. If f is exact, then you will get 0 on both sides. If f is rex, then you will get 0 here and you can continue it as 0 on this side, but not on this side. So if f is right exact, then you just want to extend it on this side, on the left side, and those are called the left derived functors. And if f is left exact, then you want to construct the right derived functors, and then you can extend it on both sides. Okay, so this is the question, and before we do anything, we will precisely use your idea and write this horseshoe lemma. Okay, so given the blue diagram, and I have to draw the blue diagram now. It is the diagram of blue diagram where the rows give amalgamated projective resolutions P dot and R dot of A and C respectively. There is a sequence, there is a projective resolution Q dot of B such that Qn is isomorphic to Pn direct sum Rn for each n, but not necessarily P dot direct sum R dot is isomorphic to Q dot. Okay, so I'm saying something that I have direct sum of projective modules at each component, but I do not have direct sum of chain complexes. Okay, so blue diagram with exact rows and columns. With exact column. Okay, let me draw the diagram. Perhaps without that you can't understand what's happening. So we have this 0 ABC, 0. Then we do the same thing that we have done so far. So P0 maps onto this. Then we have K0. Yeah, then K0 is the kernel. Then we have P1. Then there is a surjection. Then we have K1, which is the which is like this, then P2 there is a surjection and so on. Then same thing over here, here I have R2, then M1, then R1, M0, R0 and 0 and dot dot dot. Okay. So given this blue diagram, we can complete it to a diagram. The vertical thing, like these are the obvious things, I'm going to draw them in obvious way, yeah. So projective modules, you know, everything is nice. So this is P0 direct sum R0. What is the map here? P0 direct sum R0? P0 to P0 direct sum R0? The co-projection. Yeah, this is the co-projection. Then from here to here, what is the map? Projection. So that is pi 1. Okay, I should say pi 2. But I'm just going to write inclusion and projection here. I0 and pi 0. Yeah. Then similarly, I will have something here. P1 direct sum R1 and 0 here as well. This is pi 1, this is I1. And this is also same thing, P2 direct sum R2, 0 here, and then 0 here, this is I2, pi 2. Okay. Now, because you know this, okay. Now, because R0 is projective and B to C is surjective, B to C is epimorphism. So therefore, I can draw a map here. Do you agree with this? Okay. Now, from P0, you have a map to B. You first go to A and then you go to B. And from R0, you have a map to B. So the sum of those two maps is what I get here. This is the sum of those two maps, the red arrow. Do you agree? Okay. Now, I'm going to take the kernel of this. So I'm going to write all the new things. I'm going to write the kernel of this as this. Okay. Now, imagine the snake lemma situation with two exact columns. See, these two columns, P0, P0 direct sum R0, R0, A, B, C. This is exactly the snake lemma situation. So therefore, and it is like two full exact sequences, 5-term exact sequences. So therefore, I know by snake lemma that there exists this one, and then a snake map to 0, and then something in the middle. Now, what can be between two zeros in an exact sequence to make it exact? It has to be 0, correct. So therefore, you know that this map, the addition map that we obtained, is actually surjective or an epimorphism. And then you also have a map like this. Okay. And because the next part is 0, the co-kernel of map from P0 to A is 0, I can actually cut it down to a 0 here. Okay, now hide this part, hide this entire part, and imagine that this were your A, B, C, 0. Now you can repeat the process. Now once again this L0 to M0 is surjective, so therefore you will have a map here, and then you take the sum and you can continue this diagram backwards. Okay. And that's how you obtain the middle part. So it works inductively. You again have to reach the exact same starting position, and then using snake lemma, you get this. So this is the so-called horseshoe lemma because the shape looks like a horseshoe. The blue shape is exactly an horseshoe, infinite horseshoe. Okay, before finishing, I just want to give you one more definition, and that definition has to do with this red question, that how do we extend this? So, the definition now. The nth left derived functor of f from a to b, yeah, as given in the question, is denoted ln f and is defined to be the composite okay, first start with A, then you take projective resolution. Where do you map projective resolution? You map into this k bigger equals 0 proj A. Then over here I apply kf. Then I will get k bigger equals 0. Here something needs to be shown, that projective modules go to projective modules under an additive functor, yeah, of an additive functor. I'm just highlighting, and then you take the nth homology from here to B. The homology functor actually factors through this. So this is the nth left derived functor, and what do you get? Okay, the theorem says that if f is right exact, then given a short exact sequence, given an SES 0 ABC 0, in A, there is a long exact sequence which ends at this. So L0 FC, L0 FB, L0 FA, then L1 FC, L1 FB, L1 FA, L2 FC, and so on. Okay, what is the proof for this? The projective resolutions thanks to horseshoe lemma. So proof from horseshoe lemma. We get an SES 0 P dot Q dot R dot in k bigger equals 0 proj A. Okay, if f is right exact, then actually it will preserve that 0. If f is not right exact, then there won't be any last 0. Last what is missing?
The diagram is defined to be the composite over the near the top.
Oh, right. Hn to B. Yes. Okay. Thank you. So, so this is a short exact sequence. Therefore, you apply the long exact sequence of a theorem that we proved at the beginning of this lecture to this sequence, and then you get this. The important point to observe is that this is isomorphic to A, this is isomorphic, sorry, FA, this is isomorphic to FB, and this is isomorphic to FC. And this 0 is happening because it's a right exact functor. If you were dealing with a left exact functor, then you will have right derived functors, and these can be thought of appropriately as functors from the derived category. Okay, I'm not going to do that. We have already said a lot. And let me also tell you that home functor is left exact. The right derived functors of home functors are called ext functors. And the tensor functor, which is the left adjoint of the home functor, that is a right exact functor. So its left derived functors are known as stor functors. And these are some of the most important objects of study in homological algebra. Okay, let's stop here.